Hope you won't mind that. All right. So let's continue with the discussion of principles of public key crypto system. We also will look into the RSA algorithm, which is the best example of public key crypto system. Right, what's the requirement of a public key crypto system? One of the major component is this. We all know that it uses two keys. One is the public key, the other one is private key. There is always a public key, private key pair when we speak about the public key crypto system. So the requirement is it is computationally infeasible. In other words, it should not be possible. Okay, to determine the decryption key given only the knowledge of the algorithm and the encryption key. I explained this to you. You are using a public key crypto system, and you are already aware that the RSA algorithm is in action, and you have got the public key of a person because it is made public already. Having only this knowledge is totally inadequate for you to deduce the other key, which is the private key of the particular person. All right, or vice versa. So having one key and determining the other key from that available key is impossible, or in other words, infeasible. At least computationally infeasible. You'll be able to find out eventually, maybe after a million years, if you have the powerful computers. All right, that is one of the things. And either of the two related keys can be used for encryption, with the other used for decryption. This is again a requirement. There are two keys I have been mentioning again and again, where if you have used the public key for encryption of a message, the corresponding private key will be used for decryption. Otherwise, if you are using the private key for encryption, the corresponding public key will be used for decryption. So either of these key can be used for encryption, the other one will be used for the decryption. This is the generic statement about the public key crypto system. Moving on, how this encryption with public key is happening. So for that, we have got two people, Alice and Bob. So we have got Alice here, and we have got Bob here. All right. So these two people are communicating. Bob is sending something, a message to Alice, which is encrypted. All right. By looking at this, you can easily understand. I write this again here. It says Y is equal to encryption of X using the public key of A. Here, the public key of A indicates the public key of Alice. Okay. So A is for Alice, and you have got where is B? Is it mentioned somewhere? It's not mentioned here. If in case you come across B in this kind of topology, B for Bob. All right. Now Bob sends something to Alice using the public key of A. He has encrypted it. Okay. And we know very clearly how can we acquire the plain text. You are supposed to go for the decryption using something of Y. Okay. So this ciphertext comes here. So this ciphertext has to be decrypted using the corresponding key. So this is the public key of A. You are supposed to use the private key of A. All right, the other pair. So a message is encrypted using one of the keys, and we have just seen in the previous slide that the other key will be used for decryption. So in this example, encryption is done using the public key of the receiver, so that the receiver can decrypt it using his private keys. All right. Moving on, how can we do the encryption using the private key? Obviously, the private key of the sender. You cannot use the private key of the receiver. As you know, the reason is very obvious. All right. Here, the original text X is going through an encryption process using the private key of Bob. All right. So you are getting Y, the ciphertext. So how will you be able to deduce the plain text? You will be going through the decryption. You got the ciphertext, the corresponding key. So private key of B, you are supposed to use the public key of B to deduce to get X. Yes, as you know, this is a repetition of what we have learned earlier. So moving on, how can we achieve secrecy? This is again a repetition. How can we achieve secrecy? Secrecy can be achieved if you are using the public key of the receiver for encryption. Very simple. So I'm not going to dwell a long time here. But anyway, for the completion's sake, you got the original message X, which goes to the encryption algorithm. This encryption algorithm is using the public key of the receiver. B is the person called B, destination B, source is A. So what normally happens, the source A has got the private key of A, the public key of A, and the public key of B. Similarly, B will have the private key of B, the public key of B, and the public key of A. So these are the available keys. Now, person A will be able to encrypt it using the public key of B, resulting that it can be decrypted only by the private key of B, which is available only with the person B. So this is giving you the secrecy, or in other words, confidentiality. Okay. Moving on, we have the authentication. So how can we achieve authentication? Yes, we can use the private key of the sender for encryption of the message. So the ciphertext can be decrypted only by the public key of the sender. Okay, maybe the private key of A and the corresponding public key will be used for decryption. So this provides authentication. All right. Now the question is, what can we do, sir? Because public key of A is available with everyone. How can we achieve the secrecy? How can we achieve the confidentiality? We have got the answer in the screen. So generally, this public key crypto system, if you wanted to achieve, or in case your objective is to have authentication and confidentiality together, you are supposed to go for the double encryption. All right. So you have got the original message X here that goes through the encryption algorithm, and where it takes the private key of A. So I will write it here. X is taken, which is encrypted using the private key of A. All right. What's the answer? We get Y. Okay, this is what Y. All right, and then this Y is supplied to the next encryption. So it is called double encryption. So this encryption algorithm uses the public key of B. So I write it again. It is again an encryption of Y using the public key of B. Okay, this is person A, this is person B. Okay, public key of B. You will get the ciphertext. This is what the ciphertext. All right. So this is the double encryption. So when you encrypt a message using the private key of A, which can be decrypted by the public key of A, this provides authentication. When you encrypt a message using the public key of B, which can be decrypted only by the private key of B, you are able to achieve the confidentiality because no one else can decrypt it. All right. So you got the Z value, which is the ciphertext, by doing this. So how will you do the decryption? So in the decryption algorithm, you are supposed to get Y. So how will you be able to deduce Y here? You have to do the decryption, all right, of Z. So public key of B. So you are supposed to use the private key of B. So you are able to decrypt it. The confidentiality is broken now. In other words, he is able to secretly receive this message. And still, do we need to carry out this reverse of this operation? Not necessarily. If you do not want to verify the authentication, you can leave this alone. Hope you are getting me, right? So what is this decryption trying to achieve? It is able to find out the actual message because the confidentiality is included here, and you are able to do the corresponding decryption here. Hence, only P or B can be used for decryption. That is the private key of B. Only the person B is holding that key. Hence, he is able to get the actual message. Okay. Now, if you want to find out whether it is authentication, you want to achieve the authentication, you're supposed to do this. Of course, to get the plain text, you should do the decryption. But on the other hand, if you are able to get the content from this, that's sufficient. So we'll go for getting the actual X because it is in the ciphertext form. So how will you get X? Supply the Y for the decryption algorithm. Use the corresponding key. So private key of A is used. You are supposed to use the public key of A, and you will be able to deduce X. So this is how the authentication and confidentiality are achieved using the public key crypto system. All right, moving on. Right. So here I have left a space deliberately just to have a discussion. There is a person called A and there is a person called B. These two are communicating. So A is the person having the private key of A, public key of A, and public key of B. B is having the private key of B, public key of B, and then the public key of A. These are the contents which are available with A and B. Now, what are all the possible encryptions? Because one of the lines we have seen in the previous slide, which read that any key can be used for encryption and the corresponding key has to be used for decryption. You got it? So this is what the statement we saw. Now, how can we prove that? Is it valid for all the keys or it is for the selected keys? We have to find out. So let's see whether we can use these keys. Let me say, go to A. I'm telling him you can use the private key of A. So he encrypts a message using the private key of A. Let me say the message is M and the output is X. Okay. So this is the ciphertext. Okay. Because it is encrypted using the private key of A, which key can be used for decryption? Obviously, it is the public key of A. So you will do the decryption of X using the public key of A. You'll be able to deduce M. So what does it achieve? You have encrypted using the private key of A. It can be decrypted only by the public key of A. Public key of A is available with A. Public key of A is available with B. In case if there is another person called C, he also will have the public key of A. So this is providing you something called authentication. All right. So this is case one. All right. Now I go for X ciphertext, which is encryption of the message. All right. And I'm using probably the, this I have already used. I'm using the public key of A. So I'm using the public key of A to encrypt it. So how can I decrypt it? The message can be decrypted using the, because I have encrypted using the public key of A, I have to use the private key of A to decrypt it. If you could have a closer look at this, where is it going to be useful? All right, so we'll look at the usage of the key. Encryption is done by using the public key of A, and the decryption can be done only by using the private key of A. Apparently, who is the only person in this context who can decrypt it is A. Why, sir? Because look at the keychain of B. B is having only the private key of B, public key of B, and public key of A. So which key is needed to decrypt it? Private key of A. Obviously, B cannot have the private key of A, but private key of A is available only with A. Now, this kind of encryption can be done only by the sender, and it can be done only by the receiver. Of course, others can encrypt it. If this encryption is done by the sender, all right, this is a useless encryption because it can be decrypted only by him. He is the person who has encrypted. Only he can decrypt it. It is useless. Okay, at least for the communication perspective. So that is the second one. All right. So third one, probably this also we have used. We'll go for this public key of B. So you have got X, which is encrypted. Okay, so to get the ciphertext, I get the original message M, and I'm encrypting using the public key of B. So how can I deduce the message? Message can be deduced by applying the decryption algorithm on the ciphertext using the corresponding key. It is public key of B, so I'm supposed to use the private key of B. Whether this person is having private key, yes, the receiver is having the private key of B. So this encryption is having some, it makes some logic. All right. So is it useful? We'll have a look at that. Because it is encrypted using the public key of B, it can be decrypted only by the private key of B. Interestingly, only the person B in this context is having access to private key of B, and no one else can decrypt it. Hence, we are able to achieve confidentiality. All right, so it is, you are able to achieve confidentiality, or in other words, you can call it as secrecy. Pardon me if spelling is wrong. All right, so this is useful. This we have just seen, it is useless encryption. It's not going to take you anywhere. This is useful. What could be the fourth one? What is the different key which you are able to see? PRA is here, we have already used. Public key of A we have used. Public key of B we have used. Public key of B we have used. Public key of A we have used. Private key of B. Can the sender use an encryption like this? Encryption of a message using the private key of B. This is not possible because A is not having access to private key of B, which is available only with the person B in this context. So this is also not possible. So only two kind of encryption decryption is possible or useful. They are either using the private key of A to achieve to achieve authentication, or using the public key of B for achieving confidentiality. So kindly remember, you may have some questions from this. So this is the overview of your public key crypto system and the usage of keys. Moving on, where do you apply this? Okay, there are some one or two areas. Encryption and decryption, yes. The second one and the third one are new, which we haven't learned earlier. The second one is the digital signature. What is digital signature? Remember a signature. Suppose I send you office order. It is supposed to be signed by the authority at the end. Then it is valid. If it is not signed, it's not valid, as you know. So when you talk about the digital signature here, the sender signs a message. Okay, we talk about the digital signature, but remember a normal signature, sign in a paper. The sender signs a message with his private key. So signing is achieved by the cryptographic algorithm, all these things. So how can this be decrypted? By his own public key, which is available to everyone. So your authentication serves the digital signature. So as we progress in cryptography subject, we will be learning about the digital signature algorithm, and we also will come across digital signature standards, an interesting topic. Please do not miss out. And then the second major application, or probably the third major application, is the key exchange. We talk about the Caesar cipher or the classical encryption algorithm. Or in other words, we have learned about the data encryption standard. We also have learned about the advanced encryption standard in the earlier class, where the encryption and the decryption used the same key. Of course, it was using in the reverse order. That is different story, but the same key was used. Sender's key and the receiver's key were not different. It was applicable only from the public key crypto system. But data encryption standard and the AES, advanced encryption standards, they belong to the symmetric key algorithm. Sender and the receiver are supposed to use the same key for their encryption and the decryption. So how are you going to exchange the key? Because you are, I'll use this screen. You got the sender here, you got the receiver here. So sender and the receiver are supposed to use this channel for the communication. And we say that this channel is probably insecure, which indicates that the messages which are exchanged through this channel may be leaked out, or the intruders may take a copy of it, or they can disturb it. Okay, that's the reason we go for the encryption, decryption, all these operations. Now, if you are supposed to use AES, for instance, you want to use AES encryption for exchanging the data, how are we going to exchange the key between the sender and the receiver? Because unless the receiver and the sender shares the key, that's why we call it as shared key. You may remember this. Unless they share this key among themselves, they will not be able to do the encryption, decryption. Of course, encryption can be done, but it cannot be decrypted because he is not having the key which is used for encryption. So For exchanging the key between the sending and the receiving side, your public key crypto system is very, very handy. Shortly, probably in the next class, we'll be learning about the key exchange algorithm, very famous algorithm, which is given by Diffie-Hellman. Okay, so Diffie-Hellman key exchange algorithm uses the public key crypto system to exchange the keys. Interestingly, it cannot be used directly to exchange the messages. All right, so these are some of the applications areas of public key crypto system. Okay, what are the requirements of public key cryptography? Okay, I'll quickly read. You can easily understand it. It is computationally easy for a person B to generate a pair, okay, of public key and the private key. Person B or person A. If I'm the sender, I'm myself and the other side, the receiver, are using the public key crypto system. For me, if I'm called A, I should be able to generate a pair, the private key and the public key pair. I should not use the equal to symbol here. Private key and comma, okay, erase this. Okay, so this pair I should be able to generate, and it should be very, very easy. And I should not be working for ages to generate such a key pair. All right, so it should be easy. All right. Second one, it is computationally easy for a sender A, knowing the public key and the message to be encrypted, to generate the corresponding ciphertext. Very simple, sir. You have got the message M. Yes, I have got the message M. You have got the public key of the other person. Yes, I have already received the public key of other person. Now the encryption should be very, very easy to get the ciphertext. Okay, it should be very simple process, so that the algorithm should not be very, very complex, that it cannot be implemented in the hardware or software. No, it should be easily implementable. So the computation should be very easy. You cannot have complex methods, so that the encryption itself is very, very difficult to do. No, it should be very easy, provided you have got this. Similarly, it should be computationally easy for the receiver to decrypt the message. Okay, he has got the corresponding key, so he should be able to decrypt it very, very easily. So if a person holds, or if a person possesses the correct key and the text, it could be ciphertext or it could be the plain text, he should be able to easily encrypt or decrypt as the requirement may be, right? Further, it is computationally infeasible. Okay, this is again interesting. Infeasible, probably impossible. You can think that way. So it is computationally infeasible for an adversary. Adversary is the attacker. Let me call him as X. Okay, for the adversary, knowing the public key to determine the private key. So this is one of the requirements which I have said in the first slide today, that public key of somebody, maybe B in this example, is available to everyone. Of course, this person also has got a copy of this. Having this, he will not be able to find out the private key of B. No, he cannot deduce this. So it should be computationally impossible for the attacker, knowing the public key, to find out the private key. Again, it is computationally infeasible for the attacker, knowing the public key and the ciphertext, to set the original message. Something related to the previous one, but probably in a different context. Somebody has got the ciphertext. He also knows the public key of B, and it should be impossible for him to get the original message M, having these two, unless you know the private key of B. So that is something similar to that one. But anyway, sometimes in some of the algorithms, you can directly find out the plain text instead of finding out the key, because knowing the key is very much similar to getting the key of a lock, so that you can easily get into the room, open the door and get into the room. All right. So the key has to be kept secure. So availability of public key doesn't guarantee you that you'll be able to deduce the corresponding private key. If you can do that, the whole of your public key crypto system is in trouble. All right, you cannot do that. You are not supposed to be able to do that. So it is computationally infeasible. And again, these two keys can be applied in any order. Probably I'll take the example. I'll take the original message M, which is encrypted using the private key of A, and then that is encrypted using the public key of B. I'll put this, okay. to get the ciphertext. And how can I decrypt it? First, I should apply the private key of B, and then I should apply the public key of A for decryption. Okay, that's okay. Can I do this kind of encryption? Suppose I'm using the encryption of the message using the public key of B, and then I'm encrypting using the private key of A. I'll get the ciphertext. Can I do that? You can do that. How will you able to decrypt it? I'll use the corresponding public key first. Public key of A will be used by the decryption, and then the private key of A will be used again for the decryption. I'm sorry, private key of B. I'm sorry for that. For the decryption. So encryption and decryption can be applied in any order. It is a desirable characteristics, though it is not a mandatory requirement of public key crypto system. All right, so we have got to know more or less what a public key crypto system is, where the key takeaways are there are two people, A and B. They will have the key chain, where the person A will have at least two keys. One is the private key of A and the public key of A, and also the public key of B. Similarly, the person B will have the private key of B, public key of B, and the public key of A. This is the setup where the sender A should be able to prepare or generate a key pair, private key of A and private key of B. Similar private key of A and public key of A. Similarly, the other person B should be able to generate a key pair or public key of B and the private key of B. And they are also supposed to have exchanged their public keys with each other. So this is the requirement. Okay. Second step. And when you have the encryption algorithm, okay, suppose I'll say the encryption algorithm is E, which is using the private key of A for encryption, and then the algorithm should be developed or should be exhibiting a characteristic such a way that the decryption of, if it is C, the decryption of the ciphertext should be possible only by the public key of A. Then only you'll be able to get the message, no other key. So your encryption decryption algorithm again plays a major role. So designing such algorithm is very, very crucial. And we are going to learn about the RSA algorithm, very famous public key algorithm. Okay. So RSA stands for the names of the inventors, RSA, Rivers, Shamir, and Adelman, who were belonging to Massachusetts Institute of Technology, and it was made public in the year 1977. Okay, so the best example of public key crypto system. So this is the whole of RSA algorithm, very, very simple. Probably it has got some 2 or 3 steps. So the first one is the key generation by one person. So again, I'm going to bring in 2 people, Alice and Bob. Now I'm sitting on the Alice side. All whatever is happening here is on the Alice side. Similarly, Bob also will be doing a similar operation from his side. So let's see what's happening with Alice. The same thing will be happening with Bob as well, but you can easily do that. Now, step 1, we are going to select 2 numbers. Okay, the condition is these 2 numbers, we call it as P and Q. I recommend you to use the same notation when you are writing the examination or wherever you use the RSA algorithm, because they are the standard notation used. You can argue with me, no sir, I do not like P and Q, probably I want to use A and B. You can use that, but the general one, the accepted notation is P and Q. But there is no harm if you are using any other alphabets to denote that. So P and Q both are prime numbers and they are not supposed to be equal. For example, P could be 3 and Q could be 11. Prime numbers. Okay, so you should choose 2 prime numbers. We call them as P and Q. They must not be equal. All right, so they cannot be equal. So I cannot choose 3 and 3, obviously. Then step 2, I have to calculate a value called n by multiplying these 2. All right, so that's again very simple. You will be able to acquire a value called n, which is obviously greater than P and greater than Q, because it's a multiplication of these 2. Okay. And then the third step, you are going to calculate phi of n. So this phi of n will be P minus 1 and Q minus 1. You can ask a question, why is it? That's the algorithm. So this is again the multiplication, very similar to this, easy step for a computer to do. So far it is simple. Step 4, we are going to select an integer called e. Okay, this is the condition to be met. What's the condition? The greatest common divisor of e and this pi of n should be 1. In other words, e should be relatively prime with phi of n. That could be the other statement. So e need not be a prime number. E could be 4. Okay, if pi of n is 5, then you can choose e as 4 because the relative, both 4 and 5 are relatively prime. So the greatest common divisor of 4 and 5 is going to be 1. Okay, so you have to choose an integer e, not fractional number, e, such that the greatest common divisor of the selected number and the phi of n which you have acquired in the previous step should be 1. And this e again should be fall well within this range. It should be greater than 1, could be 2 or 3 or 4 or 5, whatever may be the case. And it also should be less than phi of n, and it should be relatively prime. Okay, that's the condition. You should choose e. Then we calculate d from e. All right, so d is acquired by taking this multiplication inverse of e, taking the mod of phi of n. Okay, so this I will be explaining with an example how we are now normally able to do this. All right, and then what are we having with us? We have got p, we have got q, we have got phi of n, and then we have got e. We also have deduced d. Now what is public key? Public key is e and n. Okay, so e you have chosen and n is obtained in this step. Okay, you also got n. So e and n, so this is the combination. This is the public key, and private key is what you have deduced in the step 5. D and n will give you the private key. So this is step 7. All right, so these are all the simple steps for the key generation by one of the parties. A similar step will be done by person B. So he will choose two integer p and q. Maybe same number, may not be same number, because it's all not going to be exchanged among them. Whatever is chosen by Alice will be chosen. Alice will be revealing only this. This is the public key which will be exchanged with the other person. Okay, and what is n, what is phi of n, p and q will not be revealed. It will be only with the Alice. So Bob also choose some random numbers like this. P and q both are prime number, they are not equal. Then he'll calculate pi of n. He'll choose an integer e such a way that it is relative prime with pi of n. Could be some other number. He would calculate d out of it. Then you will be able to generate the public key and the private key pair there. Okay, so at the end of these steps, A is having the private key of A and the public key of A. B is having the private key of B and the public key of B, obviously. All right, what is supposed to happen next? This public key should have been exchanged with the other person. How is it happening? We'll be learning in a separate session on how we can exchange or how we can distribute this key. Okay, so I'll take you through that. But for the time being, we assume that this is available with the other person. Moving on, how the encryption is happening. Okay, suppose now we are going to encrypt using the Alice public key. Who is going to encrypt? Person B. He is using the public key of Alice. What is public key? E and n combination. All right, so he is having the plain text which is denoted by m. So this is how the ciphertext is calculated. Simple one. So ciphertext is calculated taking the original message m raised to the power e and mod n. What is e and n, sir? E and n are the components of the public key which is already shared. And then the ciphertext will be shared over the medium, communication medium. It will reach Alice. So Alice is supposed to use his private key to decrypt it. All right. So Alice uses the private key to decrypt it. So you got the ciphertext. So you will get the original message m by taking the ciphertext to the power is raised to d, and the mod is taken for n. What is this b and n? This is the private key. It is available only with Alice. It's not available with anyone else. You got it? So this is what your RSA algorithm is. Okay, so very simple one. I would recommend you to use the same notation. I'm reminding you when you're writing this algorithm, and you also will be able to do some samples. Okay, we'll look at this with an sample. All right, so in this example, this I have taken from your textbook. It's not mine. So first step, you take two numbers which are prime numbers, and they are not supposed to be equal. So 17 and 11 are prime numbers which are chosen. So step one is fine. Then we are supposed to calculate n by multiplying these two numbers. So p and q are multiplied to get the value of n. Okay. Then we compute pi of n. So far it's simply the multiplication of numbers, p minus 1, q minus 1. So 16 multiplied by 10, it's going to be 160. Okay. Then you choose e, such that greatest common divisor of e and 160 is 1. Some number is chosen as 7. Sir, can I choose 8? No, you cannot choose 8, because 8 and 160 has got 1, 2, 4, and 8 as the common divisor. No. So the GCD of these two should be 1. So 7 and 160, they don't share any common factor. So the GCD becomes 1. So E is chosen as 7. Yeah, this is where we should concentrate little more. This we haven't come across earlier. So we are going to determine the value of D. Okay, so how are we going to determine the value of D? D is calculated like this: E inverse and mod of n. Okay, I'm sorry, mod n or phi of n? Mod pi of n? I think it is phi of n. We'll look at the this one. Yes, it is phi of n. All right. So you cannot make a mistake there. You cannot make it as n. Hope you remember this confusion. It's going to be pi of n. And this is equal to, you bring the e here, so it's going to be equal to e and 1 mod pi of n. It's going to be 160 here. You have got the e already. So d multiplied by e is supposed to be 1 mod 160. The value of e is 7. So we are going to find out a number here that is multiplied with e. Take this simple step, that will be easy. Okay, you have already chosen e, which is taken as 7. We are going to find out this number d when it is multiplied by 7, and you take mod 160, your answer will be 1. So what I used to do for this kind of calculation, when will I get 1 mod 160, or if I take modulus of 160 of that number, I will get 161. So 161 mod 160 is equal to 1. You got it? What could be the other number? I have to add 160 with this. So probably 321. So 321 is the next number. So 321 mod 160 is again going to be 1, because 160 plus 160, 320, then this 1 is available. So that also will be 1. Now, in this example, how is it done? So, it has used some number, but we'll go for the second line here. Don't look at this one. So a number called d, which is multiplied by 7, is supposed to give 161, as I said. Okay, so how will you do that? The answer is here. So 10 times 160 is no, what's happening here? D is less than 160 values. D is since okay. So you are supposed to take the mod 160. I'm sorry. Yeah, you are supposed to take mod 160. So the multiplications are supposed to be 161. But from 161, if you divide by, what is the other number? 7. Okay. If you divide by 7, what will be the number? You will get some number which is not going to be a whole number. Okay. I'll take the calculator. 160 by 7. I'm doing it for you. 160 divided by 7 is a fractional number, 22.8. So that is 161 I'm supposed to do. Yes, 161 by 7, I'm getting 23. That's simple. So 7 should be multiplied by 23 so that you will get 161. That is what the number I'm looking for. So I'll go back to the story. This is going to be supposed to be 161, which is equal to 1 mod 160. So D is supposed to be 23. So 23 times 7 is going to be 161. So this example which is taken is very simple, because as soon as I take 161 divided by 7, I'm going to get the number here. Okay. Sometimes this may not help you. You may have to go to the second number. What is the second number? 321. Okay. So you should either check with 161, or you should check if it is not giving the whole number, you should go to 321, or the third number is 160. That is 481, or you have to see again 160, it's going to be probably 64, yeah, 641, and so on. So you will have to find out these numbers, and then you have to divide them by 7 to get the number. So fortunately, in our example, by taking the first number itself, we are getting the whole number. So 23 is the other number, which means which means D is deduced as 23. Hope you got this understanding. All right. So when whatever may be the number which is given to you, you are going to take it as E and put the value as D here, which will be equal to 1 mod phi of n. All right. So if in this our example, this phi of n is 160, so and E is also chosen as 7. So we take D times 7 is supposed to be, if I take mod 160, it should give 1. That is our objective. We have to find out this number. So if you can use any method, the method which I'm using is this one. I will always look at this number. I will add this. So 161 divided by 7, I got 23 straight away. So 23 is the alternate, the other number, which will be multiplied with 7 to get 1 mod 160. So what have you got so far? We have got P, we have got Q, we have got N, E, pi of n, of course, and then D. In the RSA algorithm, when it was taught to you in the previous slide, we have chosen, I think, E and N as the private key, public key, D and N as the private key, not necessarily. You can choose one of them as the private key and the public key. So we have got that liberty. But anyway, we'll go ahead with this example. And then the public key which is chosen here is the 7 and 187. Why? It is E and N. What is E? E is 7. What is N? N is here, 187. So 7 and 187 are the public key, and he keeps the private key as 23 and 187. What is 23? We have just deduced it here. So 23 and 187 are the components of the private key. Now, what are we supposed to see? Whether the encryption by this key can be decrypted by this, or if I encrypt using this key, will I be able to decrypt it? So I have got 5 more minutes. We'll go ahead. So message is taken as M. Okay. So the ciphertext is calculated, the message. Okay. And the key values are 7 and the mod 187. What is the 7 and 187, sir? Look at this. 7 and 187. So it is encrypted using the public key of the sender. So it is encrypted by the receiver using the public key of the sender. So 88 raised to 7 mod 187 will give you the ciphertext. 88 power 7 is really a big number. All right. So to directly calculate. So we go for something called modular arithmetic. You might have known about this. Okay. Modular arithmetic. So 88 power 7 is equal to 8. You could see here, right? Yeah. 88 power 4, probably 88 power maybe 2, or 88 power 1, or 88. So that is equal to 88 power 7. So, you know, a power m multiplied by a power n is equal to a power m plus n, which we have learned it in the schools. All right. So this m plus n 7, I have just divided like this. So 88 power 7 mod 187 is also very similar to 88 power 4 mod 187, 88 power 2 power mod 187, and 88 mod 187. So that's what the calculation is done. So 88 power 4 and 2 and 1. will be able to give the same answer of 88 power 7 mod 187. So 88 power 1, which is 88 mod 187 is 88. Again, 88 mod 187 is 77. Then 88 power 4 mod 187 is 132. Now the answers are 88. You can multiply them 88, 77, 132. You can multiply all these things, and if you take mod 187, mod 187, you will get the ciphertext. So ciphertext is calculated in this example as 11. So ciphertext is 11 here. Okay, so this is what is happening in the modular arithmetic. So you please remember this formula, not formula, but this one in your mind, and you can break into pieces. So please remember, you cannot put a plus here, that will be wrong. You have to multiply them. Okay. And again, how will you be able to decrypt it? So your original message will be obtained by taking the ciphertext. What is the other value? D value is 23. We have just deduced mod 187. So if you take 11 power 23 mod 187, you will be able to get the plain text. I think you will be. Yeah, the ciphertext is 11, which we have taken from the previous screen, and the decryption formula appears here. So message is 11 power 23 mod 187. You can apply the modular arithmetic, right? And finally, you'll be able to get the value as 88, which is the message M. All right. So this is how your RSA algorithm is running, right? So can I erase all this? Yeah, I could. I'm sorry, it takes a lot of time. But... okay, why am I not able to erase certain? Some of them I could not. Okay, I think I can erase. All right, so concerning the RSA algorithm, probably you have to remember these steps. All right. Okay. So I repeat the steps. We are going to choose two prime numbers. We call them as P and Q. They are not supposed to be equal. And we are going to compute the n multiplication of these two. Then pi of n is calculated by P minus 1, Q minus 1. We are going to choose a number which is relatively prime with pi of n. Yes. And then we determine the other number D. D is equal to probably, or D is equal to E inverse 1 mod pi of n. So I have just explained to you how we have got it. So if the pi of n is 60 or maybe 50, and you want to deduce like this, 1 mod. So in this example, you always go for, if the E value is 4, for instance, we have to find out the number 4 times D should be 51. Okay, it is not possible. You cannot find a D here, because if you divide if you divide 51 by 4, you will get a fractional number. So I can go to the next number as 51 plus 50, 101 by 4. Does it work? We have to find out. It's not going to. So probably, what is that? 151. So this is the way we go ahead to find out the value of D. Okay, where you are able to get the value of D, probably we have to stop there. But anyway, in this exam, it's not going to work because it's not going to happen. Probably if you take a odd number, we can somewhere reach here. So this is how we will be able to choose the value of E and then deduce the value of D. Okay, so I can probably 5 and C. I think if I take the value of E as 3, I can easily do D 3 is equal to 51. So how will I find out D? 51 by 3 is going to 117. Yeah. So then D will be deduced as 17. So you will choose D as 17. So what will be the key values? It will be E as 3. So probably 3 and the number which I have obtained here, it could be X, and 17 and X, the number N, will be the public key and the private key. Okay. So this is how our RSA algorithm is running. So I encourage you to work out on the exercises which are given in your textbook for learning the RSA algorithm.